For all its vast emptiness, the universe is humming with activity in the form of gravitational waves. Produced by extreme astrophysical phenomena, these reverberations ripple forth and shake the fabric of space-time, like the clang of a cosmic bell. Now researchers have detected a signal from what may be the most massive black hole merger yet observed in gravitational waves. The product of the merger is the first clear detection of an intermediate mass black hole, with a mass between 100 and 1,000 times that of the Sun. They detected the signal, which they have labeled GW190521, on May 21, 2019, with the National Science Foundation's Laser Interferometer Gravitational-wave Observatory, LIGO, a pair of identical, 4-kilometer-long interferometers in the United States, and Virgo, a 3-kilometer-long detector in Italy. The signal, resembling about 4 short wiggles, is extremely brief in duration, lasting less than 1/10 of a second. From what the researchers can tell, GW190521 was generated by a source that is roughly 5 gigaparsecs away, when the universe was about half its age, making it one of the most distant gravitational wave sources detected so far. As for what produced this signal, based on a powerful suite of state-of-the-art computational and modeling tools, scientists think that GW190521 was most likely generated by a binary black hole merger with unusual properties. This newest merger appears to be the most massive yet, involving 2 inspiraling black holes with masses about 85 and 66 times the mass of the Sun. The LIGO Virgo team has also measured each black hole's spin and discovered that as the black holes were circling ever closer together, they could have been spinning about their own axes, at angles that were out of alignment with the axis of their orbit. The merger created an even more massive black hole, of about 142 solar masses, and released an enormous amount of energy, equivalent to around 8 solar masses, spread across the universe in the form of gravitational waves. This doesn't look much like a chirp, which is what we typically detect, says Virgo member Nelson Christensen, a researcher at the French National Centre for Scientific Research, CNRS, comparing the signal to LIGO's first detection of gravitational waves in 2015. 1, appearing in Physical Review Letters, details the discovery, and the other, in the Astrophysical Journal Letters, discusses the signal's physical properties and astrophysical implications. All of the black holes observed to date fit within either of 2 categories: stellar mass black holes, which measure from a few solar masses up to tens of solar masses and are thought to form when massive stars die, or supermassive black holes, such as the one at the center of the Milky Way galaxy. However, the final 142 solar mass black hole produced by the GW190521 merger lies within an intermediate mass range between stellar mass and supermassive black holes, the first of its kind ever detected. According to the physics of stellar evolution, outward pressure from the photons and gas in a star's core support it against the force of gravity pushing inward, so that the star is stable, like the Sun. After the core of a massive star fuses nuclei as heavy as iron, it can no longer produce enough pressure to support the outer layers. When this outward pressure is less than gravity, the star collapses under its own weight, in an explosion called a core collapse supernova, that can leave behind a black hole. This process can explain how stars as massive as 130 solar masses can produce black holes that are up to 65 solar masses. But for heavier stars, a phenomenon known as pair instability is thought to kick in. These pairs generate less pressure than photons, causing the star to become unstable against gravitational collapse, and the resulting explosion is strong enough to leave nothing behind. Even more massive stars, above 200 solar masses, would eventually collapse directly into a black hole of at least 120 solar masses. A collapsing star, then, should not be able to produce a black hole between approximately 65 and 120 solar masses, a range that is known as the pair instability mass gap. But now, the heavier of the two black holes that produced the GW 190,521 signal, at 85 solar masses, is the first so far yet. One possibility, which the researchers consider in their second paper, is of a hierarchical merger, in which the two progenitor black holes themselves may have formed from the merging of two smaller black holes, before migrating together and eventually merging. As LIGO and Virgo detectors listen for gravitational waves passing through Earth, automated searches comb through the incoming data for interesting signals. These searches can use two different methods: algorithms that pick out specific wave patterns in the data that may have been produced by compact binary systems, and more general burst searches, which essentially look for anything out of the ordinary. In the case of GW 190,521, it was a burst search that picked up the signal slightly more clearly, opening the very small chance that the gravitational waves arose from something other than a binary merger. For instance, perhaps the gravitational waves were emitted by a collapsing star in our galaxy. The signal could also be from a cosmic string produced just after the universe inflated in its earliest moments, although neither of these exotic possibilities matches the data as well as a binary merger. Although this event is consistent with being from an exceptionally massive binary black hole merger, and alternative explanations are disfavored, it is pushing the boundaries of our confidence. And that potentially makes it extremely exciting. Because we have all been hoping for something new, something unexpected, that could challenge what we've learned already. This event has the potential for doing that. This research was funded by the U.S. National Science Foundation. Please support our channel to grow by pressing subscribe button as well as the bell icon for daily science updates. Thank you.